Hey, this is Mrs. Sharp. Today we're going to tackle Learning Target 4.4, which deals with applying equilibrium, the concept that we talked about for a very long time, to weak acids and weak bases in solution. So here we go. Before we get into this, let's make sure that we take some time to define what acid-base strength really means and how we decide what the strength of an acid or a base is going to be. So the strength of an acid or base is not how dangerous it is or how concentrated it is. So I'm just going to make a note that this is not concentration. So just because you have maybe an 18 molar solution of something, that's wicked concentrated, but it does not mean that it's strong. It does mean that it's concentrated, as opposed to maybe like a 0.1 molar solution. The strength indicates the extent of ionization of an acid or base. So 100% ionization is required for a strong acid or base. So in other words, if you dump something into water, like hydrochloric acid, which we know is a strong acid, oops, let's add that to water, and this 100% all the way to completion, no equilibrium, becomes H3O plus and Cl minus, then you know you have a strong acid. But there are some others, ignore this for now. There are some other acids, like acetic acid, for example, HC2H3O2. When you add that to water, an equilibrium is established where you do make H3O plus and C2H3O2 minus, but you can't do what you did up here, where if this is 0.1 molar, this would be 0.1 molar. If this is 0.1 molar, this is going to be some amount less. This is going to be some amount X. We don't know what that is. And it's definitely going to be less than 0.1 molar. It's going to be a small amount. The ionization is going to make it so that don't really make a whole lot of that. Do you remember with KEQ what that would mean? If I wrote KEQ for this equation, I would put H3O plus times C2H3O2 over only this HC2H3O2, because this is a liquid, and I would have not very much of this, and I would have a lot of this in comparison, which means my KEQ would be small. That's where we're going with this. Let's back up for a second to this percent ionization constant. So percent ionization for strong acids is 100%. Okay, so this means percent ionization would be the concentration of your H3O plus divided by your concentration of your unionized acid times 100. If these two are equal, like they have been in all of our problems so far, so when you have your HCl, don't write this again, you should already have it. If this is 100%, remember we said if this is 0.2, this should be 0.2. If these are both 0.2, then that's 1. So your percent ionization is 100. If it is anything less than 100% ionization, it's considered ionization. It is considered a weak acid or a weak base. So strength is only to do with the extent of ionization, not its concentration. So let's take this idea and apply it to weak acids and come up with an equilibrium constant. We're only going to talk about acids today, and then we can take the same ideas and apply them to bases later. But Ka is called the acid constant It is very similar to KEQ. It's like a cousin of KEQ. KEQ shows us the strength of an acid at a specific temperature because it is temperature dependent. So the ones in your book, references, will show it at 25 degrees Celsius pretty much. And we're just going to assume that the temperature doesn't change in our reactions. So let's do one of these problems and see what we end up with. Let's take this acid right here, HPO4 -2. Not a bad idea in these types of problems to go ahead and write out your equation first just to make sure your mole ratios and everything like that are good. So if HPO4 reacts with water as an acid, we're going to get H3O plus, and we're going to get PO4 -3. Because this is not considered a strong acid, remember I told you the only 4 strong acids I want you to know, this is a weak acid, and we know that this is not going to happen 100%. Therefore, whatever the molarity of this guy is to start with, this is going to be somewhat less than that. So let's set up a KEQ, or what we would normally do. Set up KEQ, we take H3O plus, we'd multiply it by PO4 -3, and we divide it by PO4 -2. Because this applies specifically to acids in solution, it just gets a new name. So it is KEQ, but because it's specific to acids, we're going to call it Ka. The bigger the Ka, the stronger the acid. Because if you look at that quantity, bigger Ka would mean more H3O plus, which means it would ionize to a greater extent. Just write that so you can do a visual here. So the bigger this number is, that means the bigger this top part is in relationship to this bottom part. So the bottom part is staying the same. You're starting with a concentration. What's changing is how much of this you have. Remember, with a strong acid, you can't have a Ka. Because it's going to 100%, so this bottom number would be 0. There would be no unionized acid. It would all be this. It'd be a number divided by 0, which is undefined. But if it's getting closer to this original number, that means it's a large percent ionized, so you'd have a larger Ka. So they're all weak acids, but you can have stronger weak acids. Diprotic and triprotic acids. Each hydrogen ion has its own unique Ka and is lost individually. So let's take a diprotic acid, kind of like a cousin to the one we just talked about, H2PO4, and react it with water. So this guy's only going to lose one hydrogen ion at a time, even though this is a diprotic acid. So when it loses the first hydrogen ion, it will become HPO4, -2 plus H3O plus, and this has a Ka of 6.2 times 10 to the -8th. And there's no units on Ka. I meant to mention that earlier. No units there. When it loses its second, so when this guy goes and loses that hydrogen, it's one hydrogen ion remaining, it becomes PO4 negative 3 plus H3O plus. The Ka for that is 4.8 times 10 to the negative 13th. So they each have their own unique Ka. It happens one at a time, and we can see in this case that this acid is stronger than this acid because its Ka is quite a bit larger. So let's talk about how to actually use this. We solve what are called weak acid problems, which usually require you to find a pH of a weak acid at a certain molarity. So here's an example asking what the pH of a certain solution of acetic acid is, and it gives you the Ka. And again, the Ka changes on temperature, so it's either assuming that this is at 25 degrees Celsius, or it's telling you specifically at whatever temperature this is at. I know for a fact that this one is at 25 degrees Celsius. So just know that that changes, but this will be something you can look up in a book or will be given to you in a problem. So remember, pH is equal to the negative log of the concentration of H3O plus. And we've been working on that a lot lately, and we just talked a lot about H3O plus and the concentration from the Ka formula. In these problems, I would highly, highly recommend that you start off by writing the equation. So acetic acid is HC2H3O2. Chemists are lazy, however, and so on a lot of like acid formulas, instead of writing this whole thing out, they'll kind of abbreviate the first part of this ion's name. So you might see this written as HAC, for this being the hydrogen that's going to be lost, and this being the rest of the molecule. So I'll go ahead and write HAC for this, just to kind of simplify things. So when acetic acid reacts with water, it is going to become, to a very small extent, H3O plus, and this rest of the acetic acid molecule to the negative 1, or with a negative 1 charge. Now, if this is 0.1, with a strong acid, we could have said this is 0.1, but we can't. We can't say how much this is right now. All we know it is that some amount, but it's less than 0.1. So for right now, let's just call it X. And let's set up our Ka equation. We've got H3O plus times the C2H3O2, or the AC if we're abbreviating, minus 1 over the HAC. And let's set up our ice table. So let's take HAC and H3O plus and AC minus 1 and do initial change in equilibrium. So HAC to start with, 0.1. H3O plus 1 to start with, 0. AC minus 1, 0. Change, H3O plus went up by X amount, so we end at X. X amount, X. What happened to HAC? It went down by X, so it's going to be 0.1 minus X. It's going to be minus X actually, so at equilibrium it will be 0.1 minus X. So now we can substitute all of this into our Ka equation. So instead of H3O plus, we're going to put, and AC minus 1, we're going to put in X's. And for HAC, we're going to plug in 0.1 minus X. And for Ka, we're going to plug in 1.77 times 10 to the negative 5th. And now we've got ourselves a nice looking algebra problem. So this is really X squared. Whew, okay. Now here's the thing. Without having to factor and use the quadratic equation and all of that, because if we factored this all the way out, we'd have to solve this with the quadratic equation. It turns out that this is going to be really small. So you can ignore it. So it is going to go down by some amount, but it's going to go down such a small amount that you can ignore it. If percent ionization is less than 5%. So if this happens so infrequently that you get less than 5% ionization, which is most weak acids, then it turns out that this X can just poof be gone. So that's something we're going to double check here at the end. But I'm going to get rid of all of this now. And if I take 1.77 times 10 to the negative fifth, and I solve for X here, multiply each side by 0.1, do all of that, then I should come up with X being 1.33 times 10 to the negative third. And what is X? X is the concentration of H3O plus. This is important. I know it might seem obvious right now, but maybe later. Got to know what that represents. That X represents H3O plus. It also represents AC negative 1, but for pH, who cares about AC minus 1? We care about H3O plus 1. So we're going to plug in that number, take the negative log, and that comes out to be 2.876. So it's still an acidic solution. Come up with about 2.9 for our pH. Now what we want to do is check for a low percent ionization. So percent ionization is equal to our concentration of H3O plus divided by the concentration of our unionized acid, which in this case was acetic acid, times 100. So that is going to be equal to our H3O plus was that number that we found for X. That's 1.33 times 10 to the negative third. And we're going to divide that by 0.1. Multiply by 100. That comes out to be 1.33%, which is less than 5%. So we're okay with doing that. Let's do one more. What is the pH of a solution of 0.3 molar benzoic acid? And here's the Ka. Now, benzoic acid, you don't need to know the formula for that. We just know that it's going to lose one hydrogen at a time, and we'll just abbreviate the first part of this, so we'll call it benz. If we react H-benz with water, we are going to get H3O plus and benz minus. And it's not even important that you know the formula for that at all, because this is what we care about right here. So, okay, Ka, it'd be equal to H3O plus and benz minus 1 over H-benz. We know that this is 0.3 molar, but we don't know what this is. It's some amount less than 0.3 molar. So let's set up our ice table again and do our H3O plus, our benz, and our H-benz. So together, separate. So H3O plus to start with is nothing, benz is nothing. H-benz to start was 0.3. At equilibrium, H3O plus is going to be some amount X. So it's going to go up by X. So is benz to the negative 1. They're both going to be X. H-benz then has to go down by X. It's all 1 to 1. So equilibrium for H-benz is 0.3 minus X. So when I plug this in, I'm going to get X squared over 0.3 minus X. For now, we're going to ignore that and then check for the 5% or less ionization at the end. So we're going to set that equal to 6.46 times 10 to the negative fifth and solve for X. If you multiply each side by 0.3, take the square root of that answer, you'd get x equal to 1.938 times 10 to the negative fifth. And remember, again, that's equal to either one of these, but the only one we really care about is H3O plus. So we're going to find the pH by taking the negative log of H3O plus, which is that number right there. If I do that, I get an answer of 2.356. So again, an acidic pH. Now the last step here is to find the percent ionization. So we'll say check percent I. Make sure it's less than 5. So we want H3O plus over our unionized acid, which is going to be, we just said H3O plus was, oh, you know what? I messed up on that last slide. I'm so sorry. The H3O plus concentration was not 1.938. That's before I took the square root. It was 4.4 times 10 to the negative 3. But that doesn't change your pH. If you take the negative log of that, you still get 2.356. I know you're yelling at me right now. Get over it. All right, so I'm going to plug in 4.4 times 10 to the negative third. Divide that by 0.3. Multiply by 100. That comes out to be 1.47%. So again, well below 5%, so we are good. I have you guys try some on your own, try to get the hang of it. I will see you on Monday. Goodbye. Happy Friday, everyone. Today we're going to continue our discussion about quantum numbers. Yesterday we talked about the principal quantum number, which was basically your energy level, which was the average distance from the nucleus of that electron. Now just to recap a little bit, quantum numbers, the purpose of a quantum number is to narrow down the location of an electron. So we don't know for sure where an electron is, we only know the probable location. Wait for it, wait for it. There we go, the probable location. And that's what those quantum numbers are for, to narrow that location down. So yesterday, when we talked about that principal quantum number, we talked about that being the energy level. Now we're going to narrow it down from there. So if we know the average distance, then we can narrow it down one step further using what's called the sub-level quantum number. And the sub-level quantum number is the orbital's shape. And we haven't defined this term orbital yet, but go ahead and write it down. It's the shape of the orbital within the energy level, and the number of sub-levels is equal to the number of the energy level. I think of an electron living in a house called an orbital. So an orbital equals an electron house. It can hold 2 electrons max. So each orbital is where an electron lives, can hold 2 electrons at the most, and they are within an energy level. Now don't try to picture this in your head. Don't try to picture how there's going to be something inside of an energy level, because it doesn't work. Sub-level is a shape, and the number of shapes is equal to the number of the energy level. So let's look at this for a second, try to wrap our brains around it. The first energy level can hold 1 sub-level, so 1 shape, and that shape we're going to call S. Remember, the number of sub-levels is equal to the number of energy levels. So the first energy level, this guy right here, he only has 1 shape. The second energy level, this one here, has 2 sub-levels. So the first, the S, and then we're going to add to that a P. Now, I'm showing you some of the shapes here on the side of the screen, but we'll talk about those more in a second. The third energy level has 3 sublevels, your S and your P, and then a D. And your fourth energy level has 4. And it turns out that we don't know any more shapes than these 4. So the fifth energy level should have 5. but the only sublevels we know of are S, P, D, and F, so we don't know what that fifth shape is. S, P, D, and F are the only ones we know of. So that's the sublevel quantum number. I think we're going to talk about it a little more here. The energy of the sublevels increases. So like let's say you're in the fourth energy level here. If the fourth energy level is an S shape, then that would have less energy than an electron within the fourth energy level with a P shape. So this electron's first two quantum numbers would be 4 and S. This electron's would be 4 and P. I know S and P aren't numbers, but it's still called the sublevel quantum number. If you're thinking about narrowing down an electron's location, the city is the energy level, the street is like the sublevel. So the orbital shapes are shown here. An S sublevel has a spherical shape. A P orbital, this says dumbbell, I'm going to call it peanut. And a D orbital is a double dumbbell or a double peanut. The reason that I changed that one is because if you think of it that way, then the letter of the orbital starts with the letter of its shape. So this would be a three-dimensional region in space where the electron is traveling. So its overall path, when it's going around the nucleus, ends up looking like a sphere. So what's the difference between, remember, the second energy level has two shapes, S and P. What's the difference between a 1s and a 2s? Their second quantum numbers are the same, but their principal quantum number is different. The 1s would be a spherical, but it would be closer to the nucleus than a 2s. So a 2s would be a sphere like this. What about a 2p versus a 3p? They're the same shape, so there's a 2p, but the 3p would travel farther from the nucleus. Whoop, so far that it's off my page. So this is the path that the electron is traveling in. It could be within, remember, it's the probable location, so it's probably spinning around somewhere in this shape at a certain distance from the nucleus. So here's some more. Here's your S. Here's your P. Here's your D, your double peanut, and your F you can think of as a flower, but it's really complex. It's almost too complex to draw in 2 dimensions. The shapes I want you to know are S is spherical, P is a peanut, D is a double peanut. All right, let's jump into the third orbital quantum number. This is the actual orbital. Remember, an orbital is an electron house with 2 electrons per max, and the number of orbitals per sublevel, remember sublevel is shape, so think about houses, electron houses per sublevel shape, or we call that the street. So like how many electron houses are on that street. The S orbital holds 1 orbital. The P shape holds 3 orbitals. The D shape holds 5 orbitals, and the F shape holds 7 orbitals. Now that's just random. That's just what we know. You're just going to have to trust me on that. That's what it is. S holds 1, P holds 3, D holds 5, F holds 7. And remember, these are like electron houses. 1 electron house. So if we know 1 house holds 2 electrons at the most, we can also figure out how many electrons can be held in each shape. So for the S orbital, you can hold 2 electrons max in the S orbital, 1 times 2. In the P shape, we can hold 6 electrons, 3 orbitals at 2 electrons each. Now they don't have to hold that many. That's just the maximum amount. So D can hold 10, 5 times 2, and F can hold 14, 7 times 2. This is the electron house. So you can see that as the shape gains energy, you can hold more electrons in it. Finally, we have the spin quantum number. And the spin quantum number tells me once I'm in this house, which direction are the electrons spinning. And the only number, or the only symbol we use for the spin quantum number is a positive or a minus, showing which way they spin. Now sometimes, if I were to draw an orbital like this, just kind of as a circle that electrons can go in, instead of putting plus and minus, we would say one electron is spinning this way and one electron is spinning this way. Now remember that for two electrons to be legit, they have to have a set of 4 different quantum numbers, so none can be the same. So let's look at this. Let's say that 2 electrons are both in the 4th energy level. Let's say they're both spinning around in the S shape, so they're in a sphere. Let's say because it's the S sphere, there's only 1 electron house, so they're in the same house. But if they're in the same house, they have to be spinning opposite directions, so this part would be different. So we'll say orbital 1, spin clockwise, spin counterclockwise. So all these 3 quantum numbers match, but this last one is different. So the electrons are so close that they're in the same house, they have to be spinning opposite directions. Okay, that's it for 4-3. I know it's a lot, but we're going to practice with it quite a bit. Just try to remember for now which quantum number means what in general. Like the sublevel is the shape. Best of luck. Have a great day, and I will see you on Monday.